Go ahead, Prahladh. Yeah.
Okay. Everybody, let's get started. This will be lecture 2. So what will we do in this lecture? We will continue our, so last time we saw about 6 different applications of randomness, at least in towards computation, how it helped us to compute things faster, in some case faster, some case things which we were not able to do otherwise. What we will do today is we'll see 2 other applications. In fact, today's applications are possibly more stunning than what we saw last time. At least they are stunning in my view, and I like these 2 applications. We'll see 2 more of these applications, and then we'll go ask the main question of this course was randomness really needed in any of these applications? Can we actually, randomness was a nice tool to have. Can we get rid of randomness? And we'll take one of the toy examples for the experiment. In particular, we'll take max cut, the problem of max cut, and see how crucial was randomness there. The algorithm was very nice, but this is what will be the agenda for today's lecture. So we're going to do soon. So we're going to continue on this one. So the power of randomness, the amazing power of randomness. We'll see 2 more applications. So there was a question regarding max cut, which I sort of deferred it till the second half of today's lecture. Were there any other questions related to other applications from last time? Okay. Not. Let's get to these 2 new applications. For these 2 applications, I will need the notion of what a field is and a finite field. The field, especially in particular, I will need the notion of a finite field. And actually, the notion of a finite field will become very important in this course. We will use finite fields a lot in this course. So I thought I'll spend a good 5-10 minutes. I do not know how familiar all of you are with finite fields. So what is a field? A field, so let's just remind us. By the way, is everybody comfortable with what a finite field is, or would you like me to spend some time? Even if there's one person who wants me to spend some time.
Yeah, I would, if you don't mind, I'd really like.
Sure. Okay. So let's recall what a field is, and this one. So I'll spend some time on it. We'll post on the web page, and on Academy, we will post. So usually there is a very good primer on finite fields due to Madhusudan, no? So I will post that finite field. It has more information than we need for it. But today I will introduce what finite fields are. Hopefully at the end of this, you will know what a finite field is and what this object is. It's this abstract object. We'll get the object. And there'll be 1 or 2 properties of this object that I care about. We'll list it. And that's all. And to the best of my knowledge, those are the only 2 properties we'll use. Where they have a zillion nice properties, but there'll be just a couple of these properties of these. But anyway, let's get started. So what is a field? A field. So it's sort of going to be so we are already certain fields we know quite well. The rationals. We've been using them since the rationals, the reals, the complexes. So these are some fields. In what sense are they a field? They are a set of objects which have, so they're basically the field. Usually we'll use the letter F to denote a field object. It comes equipped with 2 operations. One is what's called the addition operation. The other is what is the multiplication operation. So a field is a set of objects, it's an abstract set of objects. It comes equipped with two binary operations. Addition. What is addition? It takes 2 elements from this set and gives you another element. Multiplication is yet another such operation. It's in the case of rationals, reals, and complexes, the exact the same notion of addition and multiplication that we know. But what is the extra property that we want of these? This one, we want F and plus. If you look at just the set with the plus, this should form a group. What do I mean by a group? If you take 2 elements, you should get another element. There should be something called what I call an additive inverse. That is, there must be an element in this set, which if you add to any other element, gives you back the other element. It's sort of like the 0 of the element. This is what we will denote as the 0. this must be an additive inverse, and every element.
Sorry, Prahladh, can you just clarify this? What do you mean by additive inverse 0?
So
meant identity.
Sorry. I meant additive identity. Boy, this is being recorded. Fair enough. So additive identity, what do I mean? That is, there exists an element which we will call 0 in F, such that for all elements A in F, A plus 0 equals 0 plus A, you get back A. That's what I mean by additive identity. The next one I want is additive inverse. That is, for all elements A in F, there exists a B in F, such that A plus B equals B plus A equals 0. You get back the additive identity. In this case, we'll usually call B to be minus A. That's the notation. We want additive inverse. Similarly, we will say F, you take off the 0 element, and with dot, this should form a group. This is a group under addition. In fact, it's a commutative group. It's commutative in the sense that what I mean by commutative is A plus B is equal to B plus A. The order of addition does not matter. All of the things which we have, these are properties which we take for granted with respect to rational reals and complexes. And similarly over here, I want it to be a multiplicative group. A group under this operation of multiplication. So once again, group under multiplication. And the additive and the multiplicative identity here we'll refer to as 1. The multiplicative identity is going to be called 1, and the multiplicative inverse we'll refer to as A inverse or 1 by A, whichever, either of them is 1 by A. Both these. But we notice multiplication has been defined only for non-zero elements. We will extend multiplication for the 0 elements also. 0 into A equals A into 0. We'll just define this to be 0. And one more property we want, that is, which is this order, multiplication distributes of, let's just call it distributive property. I do not know which one. It is for all A, B, C in the field. We must have A, B plus C equals A, B plus A, C. This is multiplication over here. These are the properties I need. Okay, this is all very abstract. I just talked about it very general. Let's actually, with the case of in the case of rationals, reals, and complexes, we all know that these are all true, and we have them. So let's actually look at some other fields which are not one of these three. So the first example I'm going to take is, now we'll start off with some finite fields. Rationals, reals, and complexes are infinite fields. This underlying set is an infinite set. We will now actually, in the next 5 minutes or so, we'll see examples of fields which are finite in size and yet have this property. So the first, so we will now see some examples of finite.
But did we mention commutativity?
Yeah. All my groups are commutative.
Okay.
All my groups are commutative.
All right.
Yeah. So for example,
I mean, I guess Abhishek's point was that commutativity is also for multiplication.
It's also for multiplication. Whenever I mean a group here, I mean, so this is also, let's put commutativity over here. So that is A dot B equals B dot A. This should be equal. So in particular, this is a reason. If you take the set of matrices of a particular dimension, that's not a field. It's a group under addition. The all zeros matrix is the additive identity under the group. And multiplication, there's a notion of multiplication defined, but it's not a commutative group. So the set of this ones don't form a field. They won't form a field for other reasons. They also don't have this notion of a multiplicative inverse, but they don't form a field because they are not commutative for us. But let's look at some finite. Let's look at some examples of finite fields. So I want to claim, let's look at integers, what's called Z mod PZ, which is integers mod P. So let's take P to be some prime number. Integers mod P. That's basically, I'm just looking at 0, 1, 2, 3, all the way up to P minus 1. I want to claim this set under the usual notion of addition and multiplication, except that whenever you add and multiply two numbers, whenever it overshoots P, you just take remainder and get it back to something less than P. This set, now if you define addition multiplication this way, this set actually forms a field on the way we have defined it. So the addition and multiplication are the usual notion of addition and multiplication in integers, except whenever you go beyond P, you take reminders and get it back to less than P. Now, it should be clear that this is an additive group. The fact it's an additive group, commutative additive group, it's a commutative group under addition should be very clear, with 0 being the additive identity, and the additive inverse of any element A is minus A, which is the same as P minus A. But now you can ask, why is under multiplication? Multiplication is well defined. Multiplication is well defined. And also it's clear that 1 is the multiplicative identity. 1 is a number which does this. I want to further say not only is this one, actually, I want to say this multiplicative inverses exist. This is the only non-trivial property that we need to check. Distributive is also clear. Distributive just follows from the distributive law for the integers. The only thing that we need to check is the multiplicative inverse. That is, every non-zero element in the group has another element such that if you multiply these two, you get 1. Which is the same as stating that for every non-zero element, there is for every non-zero element A, there's another non-zero element B, such that A dot B is congruent to 1 mod P. A dot B is equal to 1. If A dot B leaves remainder 1 when on division by P. Okay, why is this true? And this, so what the only non-trivial fact to check. Is the notion of multiplicative identity, multiplicative inverse. That is, for all A in F minus 0, this is sometimes usually written as F star. You drop the F minus 0. There exists a B also in F star such that A dot B equals 1. This is what I care for. And here is something I'm going to use without proof, but something which we know. We'll use this thing which
you meant for all A.
Yeah, for all A. For all A. Yeah, this is things which I didn't write notes before class. I assumed this was something I would do. Yeah, that's done. Fair enough. Fields, why would I need notes? Anyway, okay. So let's get to this one. Here, what we'll use is something which we have done, Euclid's algorithm, Euclid's GCD algorithm, which some of you will be familiar with. I'm going to state this without proof. A consequence of Euclid's GCD algorithm. I want to state that there's a notion of a GCD in the integers. No, let's go back to integers. That's all that work with modulo prime. Let's go with integers. There's a notion of the greatest common divisor. So we possibly And it's what is it? It is exactly what it means. I give you two positive integers a, b. There is a has a set of divisors, b has a set of divisors, and then you look at the set of common divisors. Firstly, the set of common divisors is always non-empty because one is a common divisor for both of them. And you then pick among all these divisors the largest common divisor. This is called the greatest common divisor. So this is another integer, or always at least one. And it's a remarkable algorithm dating as old as Euclid's time, stating that actually this can be, you give me two integers a and b, you can find out the greatest common divisor. There's a polynomial time algorithm that actually computes the greatest common divisor. Not only can you do that, there exists two other integers m and n such that am plus bn equals d. In fact, if you run that algorithm, those of you who are familiar with this algorithm, if you recall this algorithm, when you run this algorithm, the algorithm will output not only given AB, it will not only output D, it will actually output M and N also. It will output this triple of numbers M, N, and D such that AM plus BN equals D. Okay, let's take this on faith. This is something which some people who have done a bit of number theory or an introductory course on algorithm would have seen this. It's one of the most basic algorithms that has done. It's one of the earliest algorithms discovered by man. And it says that you give me two non-negative integers. There's a notion of a greatest common divisor, and this is a notion not only do you have it, you can actually construct it efficiently. And while doing this, you can come up with two other integers m and n such that am plus bn equals d. Now, why am I talking about this? I want to say that this is going to useful thing to recall. This was what we wanted to prove. What we wanted to prove was the statement. We wanted to check that for all a in 1 to fp minus 1, there exists a b in 1 to p minus 1 such that ab is equal to 1 when you divide by p. That is ab. Now, how do you do this? You run. So I want to say, why is this true? This is a fact which we needed to check. And the proof of this fact, I'm just going to use Euclid's algorithm. On which two integers? On a and p. I'm going to apply Euclid's algorithm on a and p. So Euclid's algorithm, what's the common? A is a number less than p. P is a prime number. What's the greatest common divisor between a and p? A is a number.
1.
1. So 1 is the game because one is certainly a common divisor. Can it have a larger common divisor? No, because otherwise p has only two divisors. It's a prime number. It's 1 or p. And a is a number strictly less than p. So p can't be the other common divisor. So 1 is the only common divisor. So in particular, Euclid's algorithm will tell you there exists m and n such that am plus pn equals 1. But this tells you that am is equal to 1 mod p. So m is our candidate inverse. So m is the multiplicative inverse of A. And sort of Euclid's algorithm gives you what the Euclid's algorithm which it did actually gives you equipped with you. It tells you how to do division. It tells you how to find inverses. This one.
No, but that chat you can ignore. I mean, there's
no. There's a reason. Okay. So Ram Prasad gave a simpler proof of it. There's a reason I did this proof because I'm going to use this proof again.
Oh, sorry. Okay. I forgot
I'm going to use
part.
this proof again once more. So there's a reason I used this. There's a simpler proof of this fact, but I'm going to use this. So this tells us that this set ZPZ is actually a field. And it's a finite field. It's finite. It's a field of size p. P is a prime number. In fact, what we've shown is for every prime number p, the corresponding ZPZ is a field of size p. And in fact, this is usually sometimes denoted FP. Math people might not like this, but this is quite common in CS literature to call this FP. Of course, I think the more appropriate one is called GFP. Okay. Any questions so far? So this is a finite field. It's a field which has all the properties that I want. It's a finite set. And this is not the only, these are not the only finite. Of course, I've shown you an infinite set of finite fields now. For every prime number p, we've shown that there's a finite field. Go a little further. But before the next 5 minutes, I'll show a further class of finite fields. I just want to know if any questions so far. Okay, if not, I'm going to look at more finite fields. What we have seen so far are these are finite fields. In fact, I want to claim for every, not just for every prime, but for every prime power, for every q of the form p power k, where p is prime and k is a positive integer. There is a finite field FQ, should we call GFQ, of size exactly q. In fact, there's exactly one finite field of this size. And in the next 2-3 minutes, I'll actually describe to you this finite field. So I will give you a description of q elements, which are these are not going to be integers modulo p to the k. It's going to be a different set of q elements. It's going to be a set of q elements such that it's equipped with addition, it's equipped with multiplication, additive. The additive identity will be 0. The multiplicative identity will be some element in this part, which we'll refer to as 1. And you have both the additive inverses and the multiplicative inverses. Okay. And furthermore, even before that, this set will have this nice property, that is, this set will have, actually, let me first define the set. So for define the set, firstly, I will look at the, so let's look at FP. FP is still our is a finite, is a field of size p. I'll use the field of size p to build up the field of size q. Q is p to the k. Let's look at FPZ, which is the ring of polynomials. Okay, I'm using the word ring here, but all I mean is the set of all polynomials with coefficients coming from this one. So this is set of all polynomials of the form taken p, I've taken q. So let's take anything of the form a0 plus a1z plus say ak z per k for any k in the naturals, in any k which is the non-negative integers, and a0 to ak are belonging to f. Take any such object, and let's go and let's look at. So once again, you have the polynomials. We're familiar with polynomials. You can sort of add two polynomials, multiply two polynomials. The usual way we do it in the reals. You can add it in this. Well, also you can FPZ. You can, there is an, it comes. Why did I call it a ring? Because it has an addition and multiplication with it, equipped with it. In fact, addition is a group. Multiplication, not necessarily, because there's no notion of it has a multiplicative identity. One is certainly a polynomial and it has multiplicative, but there is no multiplicative inverse. Certain polynomial, certainly the polynomial x, there's no other polynomial I can, if I have the polynomial z, there's no polynomial I can multiply z with to get back 1. this is not a group. But what we will do is, so let's take some exhausted all my. So let's take a polynomial f. Let's take some polynomial a1z plus akz per k, which happens to be an irreducible polynomial. What do I mean by this? I haven't formally defined it, but what do I mean by irreducible polynomial? What I mean by an irreducible polynomial is given you can take two polynomials, multiply it to get another polynomial. Now you can ask the other process. It's just take a polynomial, can you break it up into factors? An irreducible polynomial is just like a prime. In the case of integers, it's a polynomial which you can't break up. Its only factors are 1 and itself. It cannot be broken up into parts. That's what I mean by an irreducible polynomial. And let's look at further. Let's actually make this guy a monic irreducible polynomial. That is, it's monic. What I mean by that, its leading coefficient is 1.
So here we also have the constants as factors, not just 1, but you also get those, 2, 3, 4, everything also. That is also a factor. Any constant, non-zero constant.
Any constant is a factor. Any constant is a factor. Yes. Any constant is a factor. Yes. Okay. What I want now to do, let's look at the set S, which is FPZ. Just like we took the integers modulo the primes, we took ZPZ. We took the integers modulo a particular prime. I'm going to take the polynomials modulo this particular irreducible polynomial. More precisely, I'm going to look at this object. This is just setting, it is just the set of polynomials modulo fz. So you take any polynomial, just go mod fz. So the set of all polynomials are only the possible. Notice once you go mod, the only possible remainders are at most polynomials of degree at most k minus 1. When you take when you're going to get a polynomial only of degree at most k minus 1. Therefore, the size of S, in fact, the size of S, you notice is exactly going to be p per k. All the polynomials of degree up to k minus 1 occur in it, and everything else will get reduced to one of these. So this is this. And in fact, we are going to show S is going to be our finite field. S is going to be our field FQ. The field FQ is exactly going to be this set yes. But this set yes, I need to equip it with an addition and a multiplication. The addition and multiplication are going to be exactly the same addition and multiplication that we have seen so far. Addition is the addition of polynomials. Multiplication is the multiplication of polynomials. And you do exactly what you did in the prime case. That is, if either of them overshoots the degree, the appropriate degree k, you just take remainder with fz and get it back to less than k. So exactly as you did it in the case of the primes ZPZ, you had the integers. Whenever you did, you just imported the addition and multiplication from the integers for the finite field of prime numbers, and whenever it overshot p, you just reduced it mod p. Here you will do the same thing. Addition and multiplication is going to be addition and multiplication over the underlying of the polynomials, but whenever you shoot k, you just reduce it. You take a remainder with the polynomial fz, and that's the resultant. So it inherits addition and multiplication from the ring FPZ. Okay. Any questions so far? People who are familiar with finite fields, this is very basic stuff, but I just want to, because we're going to be using finite fields repeatedly over and over again. We're going to use this object again and again in this course. So I thought it's best we are on the same page. We know what a finite field, and I say a finite field, we know what it is. So this is the object I'm going to be referring to. This, yes. It's a set of polynomials mod f. So we already have equipped it with addition. We have equipped it with multiplication. Clearly, it's an additive group. It's a group, it's a commutative group under addition. 0 is there is 0. You take two polynomials, you add it, you get another polynomial. You take just negate all the coefficients, you get the additive inverse. So under addition is very clear, it's a group. Multiplication, once again, the only non-trivial fact to be checked. We checked is yes is a group under multiplication. More precisely, exactly the same problem we had before. That is, for all A in S, there exists a B in S such that AB equals 1. Or equivalently, for all polynomials G of Z in S, there exists another polynomial H of Z in S such that G of Z times H of Z is congruent to 1 mod F of Z. That's what we need to show. That is, you give me a polynomial. Notice polynomials, if you didn't have this mod operation, polynomials don't have a multiplicative inverse. I want to give me a polynomial A of Z. I want to say I can multiply it by another polynomial H of Z. Actually, let me just use A and B. A, P, A, Z. You give me a polynomial A of Z. There exists another polynomial B of Z, so that when you multiply it, the product polynomial is obviously it's not the one polynomial, but it is a polynomial which, when you divide it by F, leaves remainder 1. And the proof of this is identical to the proof of the other. There is a corresponding Euclid's algorithm for polynomials. And the proof of this is use Euclid's GCD algorithm now for polynomials instead. What do I mean by this? What do I mean by this? That is, Euclid's GCD algorithm says if you give me two polynomials, AZ and BZ, now BZ, there is once again there's a notion of DZ, which is the greatest common divisor. Polynomials also have factors, so you can pick up the greatest common factor. And Euclid's algorithm actually gives you this fact that there exists polynomials MZ and NZ such that AZ times MZ plus BZ times NZ is equal to DC. Okay. If you give me two polynomials A and B, and their GCD is D, there exist two other polynomials M and N, such that AM plus BN equals D. Now you do exactly the same thing. If you want to find the multiplicative inverse of AZ in the set S, what do? Let's look at the GCD of AZ and FZ. Once again, what's the GCD of these two objects? One is certainly a common divisor. One is a common polynomial. Is there a polynomial of larger degree than this? Can there be a polynomial of larger degree? Have I lost people or?
No.
Why?
Because FC is irreducible. We started off. So FC is irreducible.
Yeah. So
the largest like element of the field, since it's finite.
No. So these two guys, if they have any, certainly one is a common divisor. Now, is there a polynomial of larger degree than one? If that polynomial is a common divisor, it's also a divisor of FZ. But FZ, we said it's irreducible. So its only factors are 1 and FZ itself. And also all scalar multiples of this one. So there exists no other this one. But FZ is not, AZ is a polynomial of strictly smaller degree than K. It doesn't, it's degree at most K minus 1. So FZ can't be the common divisor. So in particular, the only guy is 1 again. 1 and scalar multiples of this. And now you just appeal to, so hence there exists by Euclid's will tell you exact same Euclid's algorithm will give you that there exists M and N such that AM plus BN is 1. Sorry, AM plus BF is 1. BF is 1. But that's it. Now you have AM, AZ into MZ is congruent to 1 mod FZ. So M is the multiplicative inverse. Why did I do all of this? There are easier ways to do this, but this one tells you not only is there exists, you can actually find it efficiently. Euclid's algorithm is an efficient way for doing division. So it tells you, I give you A, you can find the multiplicative inverse of A efficiently. It's an algorithmic procedure to do this. So this sort of, so hence the conclusion of all of this is S is a multiplicative group. S is a group under multiplication. So the S star, if you remove the 0 element, is a group under multiplication.
Sir, I had a question.
Sure.
Yeah, what do we mean by greatest when it comes to polynomials here? I mean, I understand the degree part, but there are coefficients involved.
Greatest here. Okay, so that's a good question. You should have asked. I sort of slipped it under the rug. So whenever we have this, so in the case of integers, greatest, we are going to define an ordering among the integers. There we define the value, the size of the integer. That's how greatest came. Here, the greatest is going to be about degree. So I want a factor of as high a degree as possible. Now you can ask, there can be 2 factors of the same degree.
Yes.
They would just be scale. If there are 2 factors the same, they will have to just be scalar multiples of each other. Not necessarily. Is that so? It's not true. They can be 2 common divisors of the same degree, which are not scalar multiples of each other. But it's not hard to see that the greatest common divisor, there will be only one of them, and all the others will just be scalar multiples of each other. So the greatest common, this is a fact to be checked. It's not, it doesn't follow from what I have said. It needs to be checked. It's possibly easy check. So greatest here means greatest with respect to degree. Okay.
And choice of F doesn't, so it would give the same question.
Yeah, so this is an important question. So I have defined this one based on I gave you S based on what a particular irreducible polynomial. Now a different irreducible polynomial of degree K could give me a different S. It so happens that all of these are actually the same object. That is, they look different to you. The way the representation of them are different, but they are all the same. It's just like you have the complexes, whether you called it I or minus I, you get the same object. Similarly, these are just different isomorphisms of the same. It's just a different way of writing it, but actually you get exactly the same object as. This reads a proof. We'll not do this, but I don't think we will ever use there is the unique finite field in any of our applications. We'll just use a finite field. So this is a finite field of size Q, and this will suffice. But actually it is unique. It doesn't, the choice of F does not, whichever F you choose, the set yes you get will all be the same. It will be the same set of operators. You'll get the same set back. Okay.
So is there some easy argument to show that there exist irreducible polynomials of any given degree in FPZ?
Of any given degree, 1 second, is there an easy way to?
Or even arbitrarily large degrees, is that easy?
Arbitrarily large degree won't this one end set in? Can't you do just the primes are infinite proof? Can't you copy that proof?
Yeah, I think so.
That you can copy.
Yeah.
For every degree you want an irreducible. That's true. I want this. How do I prove this? Okay, I should have thought of this beforehand. I don't have a. Ram Prasad, do you have a quick way of?
I think there are these, what are they called? Eisenstein criteria or something. You can maybe use those to just construct explicit irreducible polynomial.
No,
That
in
may
fact,
be
I
one
do
thing.
know. I do know. You give me
The
P, I
other
can
thing
tell
is
you-
probably there is some counting argument type thing, right? I don't recall right now, but there's a way of just counting the number of irreducible polynomials and getting a recent estimate. But I guess the question is, when does this asymptotics kick in? Probably, but yeah, I can think about it and get back. Yeah.
Yeah. So there, yeah. So this uses the fact that for every degree k, there is a irreducible polynomial of that degree k. In fact, there are several of them. You use them to do this. So one other fact that we will use. So two other. Okay. So this is, so all I told you. So what does it mean to say I have a finite field of size? By the way, so we have shown, what have we shown? Besides the 3 infinite fields that we talked about, I have talked about several finite fields. We have talked of finite field of every order, of every order whose size is exactly every prime power to the k. It so happens that these are the only finite fields. Every finite field corresponds to some prime power, and in fact, it is exactly the field which we talked about. These are all the finite fields. There are no more finite fields. Every finite field has to be of size some prime power, and then the way to get it is to take the ring of polynomials of FPZ, quotient it with an irreducible polynomial of degree k, and what you get is that finite field. All you might be doing is, it depends on, as Shubhada asked, it might depend on which irreducible polynomial, but these are all equally isomorphic to each other. So these are all the finite fields that we have. So when the moment, why am I saying all this? When in a problem statement or in this one, when you say given a finite field, what does that mean? Given a finite field, that means firstly you're given the number p and you're given this irreducible polynomial f. So you're given both this. So when I say given a finite field, that means you're given p, which tells you which prime power you're working with, and you're given an irreducible polynomial. So once you have this, you know how to operate in the field. That is addition, multiplication, division, subtraction in the field are easy now. The addition is just polynomial addition. That's just, we know how to do polynomial addition. Multiplication is also polynomial multiplication, and then followed by taking a remainder if you overshoot the degree. Division, you use Euclid's algorithm to do division. So when I say given a finite field, this is what it means. When I say given a finite field, it means given a number p and an irreducible polynomial of degree k. So when I say given a finite field of size q equals p to the k, what it means is I give you a prime p and a corresponding irreducible polynomial of degree k. And you can then do addition, multiplication, everything in that particular finite field. So just let's say, so the representation for us, the representation of a finite field fq will be the prime p and the irreducible polynomial q, where q is fp, q is p per k, is the irreducible polynomial fz in fpz of degree k. Okay, that's what the representation. When I say given a finite field, it just means this thing. I give you p and I give you this irreducible polynomial. I have said all this. I need 3 other facts about finite fields that the only 3 facts. Having said this, only 3 facts of finite fields I think I will use in this course. One is the first is what I'm going to call. So three basic property, 3 properties of the only 3 properties of finite fields. Besides the fact that efficient addition, multiplication, division, subtraction exists, that I already proved to you now. Besides that, the only properties of finite fields that we will use, that we will hopefully use in this course, that we will use is the following. I'm going to prove these with, I'm going to assume this without proof. First is what I'm going to call the degree mantra. Is let f of z. Now f of z is now a polynomial possibly I should not use f of z. Let's use g of z. G of z is a polynomial whose coefficients come from the finite field fq. And the degree of g is less than or equal to d. Let's call it is exactly d. Then g has at most d roots. This is the degree. I'm going to say, if you give me a polynomial of degree d, it cannot have more than d roots in this particular finite field. That's the first of the properties I'll use. I'm going to use this. By the way, all of these are true. These properties are true over the reals, complexes, and this one. You just the corresponding versions are also true in the finite fields, and this is all we'll be using. And we'll see actually some instances of this later in today's lecture itself. That's the degree mantra, which will be actually we'll use this repeatedly during this course. Degree mantra. The next will be sort of solving linear. It will be related to solving linear systems. So suppose I give you a set of equations of the form a11 x1 a n1 xn equals 0, a21 x1 a n2 x2 xn is 0. So I give you m such equations. Possibly I should have swapped the row and column things, but right. So I'm giving you a system of m equations in n variables. The variables being x1 to xn, and the coefficients are coming from coefficients, that is the aij's, are all sitting in the field fq. I want to say that if m is greater than or equal to n, let's actually make it m greater than n. Like I say m greater than or equal to n. If the number of constraints is at least the number of variables, this system always has a solution. This is something which we've seen in linear algebra because this property of linear algebra that holds in the reals, rationals, and complexes, I want to say it also holds for us in the finite field. And this is something which both the degree mantra and this seem like extremely obvious things. And this is all that we will be using about fields for the most part of this course. That is, so what I'm saying is m is greater than n, then there is a solution to the above system, to the above linear system. In fact, the space of solutions if you don't follow this, you can ignore this for now, is a vector space of dimension at least m minus n. This is something, by the way, this is something, if you've done any bit of linear algebra or the reals, complexes, this one, you would have seen this is obviously true. And I say the same statement just is true over here also. This is the fact. It is a solution. Okay. The third thing I want to say is FQ is a finite field. Then I should have thought once before doing the class. Then every A in FQ satisfies x power q minus x equals 0. Sorry, Sushant, you're right. It's the other way around. The number of variables should be more than the number of constraints. It should be an under constraint system. And this is so erase and minus infected. Okay. So I give you a finite field, this one. Then I want to say that every element A in FQ actually satisfies this equation, x power q minus x equals 0. And in fact, now by the degree mantra, you can show that these are the only guys that can satisfy this, because there are q elements in the field, and these are the q. This guy can have only, these are the only solutions to this. They can't have it. All the solutions to it are exactly, so in fact, all the roots of xq minus x are the set of roots of xq minus x are exactly the field FQ. This is, I'm assuming I'm working. Yeah, this is exactly using just these three properties. Okay, I vastly underestimated my time. I thought I'll finish this in the first 15 minutes to give an introduction to fields. The first 45 minutes, or possibly the 1 hour. Yeah. Okay. So this is what I mean by a finite field. No, but it's good that we spent so much time, because we are going to be using finite fields repeatedly, even in the rest of today's lecture. Repeatedly, it's next lecture, following lecture, we'll be using finite fields all the time. But we need to know what a finite field is. So finite fields are sort of, you're taking the same thing from same object as real complexes in this one, finite size. The first classic examples are the prime fields, fields of size, fields whose sizes are the prime numbers, and these are exactly integers mod primes. But then we say that these are not the only finite fields. There are other finite fields too. For every prime powers, you also have finite fields. And what are they? One way of constructing them is take the ring of polynomials over the prime fields and quotientate it with an irreducible polynomial of degree k. You get this, and it just inherits addition and multiplication from the ring of polynomials. And Euclid's algorithm tells you how to do division or the multiplicative inverse in both the case, both for the prime field as well as the prime power field. So this is what we mean by a finite field. So when somebody says given a finite field, there's a whole thing of this in the background. When they say given a finite field, it means they give you a prime p, they give you an irreducible polynomial k, so that addition, multiplication, everything is efficient over this finite field. This is what it means. Okay. Okay. So that sets us the pace for the two applications I'm going to be talking about. Any questions on finite fields? But yes, I'll put in a more detailed primer on finite fields. You can look that up for more properties of finite fields. Any questions? And the only property of finite fields we will be using is the fact that finite fields, you can do addition, multiplication, subtraction, division efficiently. And they have these three properties. The degree mantra, that is any degree d polynomial has at most d roots. Linear system, if the number of constraints is less than the number of variables, then there always exists a solution. And furthermore, the space of solutions is of dimension n minus m. And x power q minus x is a polynomial equation which captures in it all the roots, and exactly the roots of captures in it all the elements of the finite field FQ, and exactly those elements, nothing more. Okay. Okay. Much for this. Let's go on to let's go back to resuming the power of randomness. Next, so we go on to application 7. This was called the polynomial identity test. So what's the problem here? The problem here is the following. So let F be a field. Here, this could be either a finite field or an infinite field. I don't care. And given two multivariate polynomials. Now, in this case, I'm going to work with multivariate polynomials. Multivariate polynomials. Say, what should I call it? Let's call it capital P and capital Q. So these are two multivariate polynomials over the field F. So there are polynomials over, say, M variables. Check if they are exactly the same polynomial. What does this mean? When you write, it's a polynomial, so it has a coefficient representation, and the coefficient representation P and Q exactly are exactly the same polynomial. This is what I want to check. So that's the problem here. Now, immediately when I pose such a problem, you should ask, what does given mean? How does the polynomial give? How do you give the polynomial to you? When you said given a finite field, I told you what does that mean? That means give you a prime P, irreducible polynomial K. What does given two polynomials mean? There are multiple ways. So let's ask, what does given mean? Given means one way of saying given is I give the polynomial as a list of coefficients. So if I give you the polynomial as a list of coefficients, then how easy or how hard is this problem? I just need to check the polynomial P and the polynomial Q are the same. And I give you the polynomial as a list of coefficients, the polynomial Q as a list of coefficients. How easy or hard is it? To motivate yourself, think of your univariate setting also.
It's trivial, right? You just compare.
Yeah, it's trivial. You just look at this list and that list and just check every coefficient by coefficient if they are the same. So if this is what given means, if this is how the given means, this is trivial. In this case, the problem is trivial. So this is not what I mean by given at all. So in this case, there's no, the problem is trivial. The other case is what we usually call the oracle case. This is sort of a bit ambiguous, but so I don't give you P and Q explicitly. This is what I said is list of polynomials is what is meant as list of coefficients is sort of the explicit description. I've given you it in all its ugly details. I opened out the polynomial. Suppose I give you an oracle. In other words, I give you P and Q in terms of you can query it at any point. You query it at the point A1 to AM, and it will tell you what the evaluation of the polynomial at the A1 to AM is. You query it at some other point, it will tell you. So it's an oracle in the sense you don't give it as a list of coefficients, but you give it as some object which you feed it any input, it will tell you what the evaluation of the polynomial at that input is. So it's sort of an oracle. You ask a question, it tells you what the answer to it is. So suppose I give you P and Q as oracles instead. One way of implementing such an oracle is actually I give you sort of the arithmetic formula. I'll explain what this means, that computes P. That computes P and Q. In other words, for example, the polynomial x square plus 2x plus 1, I could have given it as I could give the following arithmetic formula. I give multiplication, then I take x multiplied by 2. There's an addition, this, and 1. So this is sort of a formula which takes in whose leaves are, it's sort of a tree-like structure whose leaves are the variables, or the field elements, and the intermediate nodes are plus and multiplication gates, addition and multiplication gates, and you compute the polynomial this way. So I could give you the polynomial this way. I give it to you as an arithmetic formula and say this is it. Certainly, if I give this, you can compute, you can I give the polynomial this way, you can certainly compute it at any point because you just plug it in and every time you just carry the value up and you know how to do addition and multiplication in the field, you can do this. So this is one way of doing it. Now I ask you, now can you check if P and Q are the same polynomial or not? Now is the previous case when I said list of coefficients, it was trivial. Does it still continue to be trivial in this case?
For univariate setting, I think maybe if we take just a random point.
Yes.
So if the degree is d, so two d degree polynomials can't vary more than d points. So
Yeah.
for a random point, it should be correct with probability 1 minus d over the size of the field.
Yes. So precisely. So good. So we're going to use the degree mantra. So let's restrict to the univariate setting, as you said. That's exactly, and we will extend the same idea to the restrict to univariate setting. The univariate setting, the degree mantra told us that the number of roots of a non-zero of a degree d polynomial is strictly less than or equal to d. It can't be more than d. Now p minus q, if p's maximum degree was d and q's maximum degree was d, p minus q is also a polynomial of degree d and it is non-zero. Here is the number of roots of a degree d. It's important that this is non-zero. Otherwise, if p were equal to q, then p minus q is the all zero polynomial. If p is not equal to q, p minus q is a non-zero polynomial of degree less than or equal to d. So what Amit just now said is, in the univariate case, if p is not equal to q, if I pick a random point A in the field and I look at PA equals QA, this will always be less than or equal to d by the size of the field. This is the same as stating that probability p minus q, this polynomial evaluated at point A, is 0. I pick a random, this one. So this is when p is not this one. When p is identically q, certainly we have that for every point A in F, we have PA equals QA. This happens with probability 1. So this such as a very natural, this one is, if you have a bound on the degree of the two polynomials, then an easy way to check if they are the same or distinct is just evaluate the two polynomials at a random location. Now, if they were actually the same polynomial, the evaluation obviously is going to be the same. With probability 1, you will get, this is what this one is stating. With probability 1, if the two polynomials are the same, you will get, their two evaluations will be the same. If the two polynomials are different, then they are going to be the same only with probability. They can be at most d roots. There's only there would at most d places where they can be identical. So if you pick one of, if you happen to pick one of the other points, then certainly you're going to observe that the two polynomials are different. By the way, this fact did not need, if you recall, this did not need the fact that you picked a random point from the field. It could have been any set, yes. And we have this fact, where yes is any subset of the field is. Because in the univariate case, we knew they were exactly d roots. Therefore, the number of places they can agree is at most d by the size of p. Okay. So this was the univariate setting, as we said. Now I want to know if the same thing holds for the multivariate, and surprisingly the same of what about, we are asked what about the multivariate setting. In the multivariate setting, suppose what I'm asking, in the univariate setting, I said if a polynomial has degree d, I asked you how many roots does it have? It has at most d roots. And you can ask, is the same thing true in the multivariate setting? If a polynomial has degree d, how many roots does it have? Now this d is not no longer a bound on this. For example, even let's look at even the rationals. My example of a multivariate polynomial is say x minus y. X minus y has infinitely many roots. Every pair a comma b where a equals b is a root of this polynomial. So you cannot bound the number of roots of this polynomial as we did in the univariate setting. The univariate setting, we had that if you give me a degree d polynomial, the number of roots, if a non-zero degree d polynomial has at most d roots. We had this. This is no longer true in the multivariate setting. But what happens to be true is the exact statement which we wanted to prove used in the univariate case. What Amit had suggested is, so let's say what is not. So question, the degree mantra, what I want to say is, the first observation I want to say is, the degree mantra is not true in the multivariate setting. And that's important to notice. You can't put a bound on the number of roots. But what is true? But the following is true, which is good enough for us. That is exact same thing. That is, let me write it. So P is a non-zero multivariate polynomial. And so P lies in F x1 to xm. S is some subset of the field F. And now I'm going to pick a random A1 to AM in the grid S cross S cross S cross S. We could also take an F to the M. And I ask, what happens when I evaluate P at this location? Multivariate polynomial of degree less than or equal to T. This statement continues to hold. And this is what is called, this is a statement which has been discovered and rediscovered several times over. It's a very easy statement to prove, but it's been discovered several times. So it's called the Schwartz-Zippel Lemma. It's called the polynomial identity lemma. There are several names for this. The two instructors, I think, will use different names for this. But once you have this fact, now you can do exactly the same algorithm which Amit suggested for the multivariate setting also. Just if two polynomials, if you want to check two polynomials are equal, just pick a random, just choose a grid of large enough size, much larger than the degree of the underlying degree of the polynomials. Pick a random point, check if the two polynomials, evaluate the two polynomials, check if they agree. If they agree, you say yes. If they don't agree, you say no. And what's the probability of error? It's exactly this. So it's we have exactly the same thing. So even in the multivariate setting, the following algorithm, even in the multivariate setting, we have the following case. If P is equal to Q, then probability when you pick A at random, A bar at random from S to the M, P of A equals Q of A. Of course, this is going to be equal to, it's with probability 1. This is a case. If P is not equal to Q, then probability, the same probability P of A equals Q of A bar. this is less than or equal to d by size of s. So if size of s is considerably larger, this gives you a randomized algorithm to differentiate the two. The Schwartz-Zippel lemma is an easy lemma to prove. It just follows inductively from the degree mantra. I'll give it to you in the first problem set. Of course, this is something which is it's good to actually do it yourself. I can do it in class right now, but it's easy if you actually do the proof of it to yourself. Just write the proof of it. It just follows. It's an inductive statement which follows from the degree mantra. The degree mantra gives you the base case of the induction, and you just induct on it and you extend it for the multivariate setting. So this version of the induction, this extension does not work. The degree mantra as such doesn't work. But if you state it as a probability statement, this extends to the multivariate setting. And this is what's called the Schwartz-Zippel lemma or the polynomial identity lemma. And this lends you this randomized algorithm to check if two polynomials are equal or not. Okay. I made a big fuss of this thing. It's an abstract thing. Who cares whether two polynomials are equal or not? This is a problem. I'll now instantiate this for a specific setting and a very surprising setting and show how this is actually useful in something related to give you some problem related to graphs in which this randomized algorithm is useful. But before that, I just want to take questions. Any questions so far?
So without knowing a degree bound, is it useful?
No. So you need a degree bound on this. For instance, just if you just take even in the univariate setting, if the degree was as large as q, and if you're picking points in the field, if the polynomial happened to be x bar q minus x, there's nothing you could do. You'll always get the polynomial 0. The evaluation will always turn out to be 0. You will not get, it will not give you, because you're viewing the polynomial only by its evaluation. You're not viewing the polynomial as it is a non-zero polynomial. X bar q minus x is a non-zero polynomial. But if you just view it as evaluation, you will never realize it's a non-zero polynomial, because the degree bound has to be smaller than the set S from which you're picking this rank space. Yeah. And the same thing, and the similar thing holds good for in the multivariate setting also.
Yeah, and the Schwartz-Zippel does not really require the field to be finite, right? You just need that.
Yeah. The Schwartz-Zippel doesn't require the field to be finite.
Yeah, okay.
So whenever there's a case of finiteness, I will actually say FQ. Otherwise, I'll say F, which works for, I think I will follow this principle. Let's see. So Schwartz-Zippel does not need finiteness of the field. It just uses the degree mantra, but the degree mantra is true both for finite fields, infinite fields, and it just uses that as a base case, and then you can induct and prove it for the M-variate setting. Any questions? Okay. So this is sort of the previous polynomials all we talked about seemed like natural things. This is a problem that comes about when you talk about polynomials and stuff. But why do we care about this? We will see. Let's see an example. I'm going to now talk about an application of this. So this will be, it's going to be actually a sub-application of this, but it's important of its own right. So let's call to bipartite matching. So what's the problem here? Problem is, given a bipartite graph, given a simple bipartite graph, G is L R E. What do I mean by that? So I give you the left side, I give you the right side, and I give you the set of edges. Want to ask question? Does there exist a perfect matching that is, can I pick a subset of the edges so that every vertex in L is mapped to every vertex in R and the other way around, and exactly one vertex? This is sort of a matching. It's a permutation. That is, there is a underlying So you can, so how do I write this? So there's an, so there is an underlying match. There's a matching edges. You can match. So every vertex here is uniquely mapped to a vertex here, and I'm not stating this correctly, but you follow what I mean by a perfect matching. I want to ask, given a graph, given a bipartite graph, does it have a perfect matching, which matches all the vertices in L and R? If you've seen an algorithms course, there are very nice algorithms, one of the prettiest algorithms, the earliest algorithms that tell you how to find this bipartite matching. This one, what we will show is those algorithms, and they were involved algorithms, they're not easy algorithms. What we'll show is now using the previous Schwartz-Zippel Lemma, the application to polynomial identity testing, will give actually an extremely simple application of this, which gives you, will show you, demonstrate the power of randomness. I'll be able to answer whether this graph has a bipartite perfect matching or not by just tossing a few random coins. Is the problem statement clear to people? If not, let me know. So the problem is, given a graph G, a bipartite graph G. Firstly, for this statement to even make sense, L and R should be of the same size. So let's assume that, because otherwise there can't be a perfect matching. So let's assume that size of L equals size of R equals N, because otherwise there can't be a perfect matching. So we're going to have the left and the right hand sides are equal. And now I want to ask, is there a subset of the edges, of the given set of edges, which so that there's a perfect matching between them? Okay. Okay. So what we will do is, I'm going to construct this. I'm going to construct a new matrix M. So first, let's look at let's look at the what's called the adjacency matrix, the bipartite adjacency matrix of this graph. So A, this is it's an n by n matrix, which this side corresponds to L, this side corresponds to R, and Aij is 1 if Ij is an edge and 0 otherwise. So it's sort of just a representation of the graph. This is what I call the bipartite adjacency matrix. It's a 0-1 matrix. Now I'm going to come up with AZ. I'm going to come up with a matrix whose entries are not 0-1, but whose entries are going to be either 0 or variables. And how many variables? I'm going to put as many variables as there are edges in the graph. So AZ will also be an n by n matrix of the same, it's going to be exactly the same dimension as before. This will correspond to L, this will correspond to R. Aij, so sorry, this matrix. AZ is a matrix of Ij. The ijth entry of this matrix is going to be not 1, but it's going to be the variable Zij if Ij is in edge, and 0 if Ij is not an edge. So for every edge, we'll give a new variable and we'll replace the 1 in the previous bipartite adjacency matrix with this new variable. So it's a matrix of, so it is some such matrix with all variable entries in it. Is the matrix definition clear to you? So let's look at this matrix. Why do I care about this matrix? Now let's look at let's look at the determinant of this matrix. Some of you know, if I give you a matrix M, what is its determinant? The determinant of M is exactly, you go over all permutations sigma in Sn. It's this, it's -1 to the sign of the permutation, the product of Mi sigma I. So So what is a permutation? What is you might be familiar that this is what the definition of a determinant is. What does it do? It takes every possible, notice that this object, what we are doing is exactly, it's sort of like a matching. It goes over all possible matchings. It takes, so let's assume we have a complete graph now. This one, it looks at the matching looks at the matching specified by sigma. Sigma is a candidate matching. There are n factorial matchings based going over all SN. It looks at mi sigma I, this product over just over the edges corresponding to this matching, multiplies all of those values, corresponding entries in the matrix, and then multiplies it by the sign of the permutation. This is what the determinant is. For a general matrix, what is determinant of AZ? So what is the determinant of AZ? In fact, all I want to ask is the fact, if the graph does not have a bipartite perfect matching, what will be the determinant of AZ?
That would be 0.
It will be 0. So only observations that I want to make are the following. Fact is, if G has no bipartite, has no perfect matching, then that's the first observation. Then determinant of AZ is identically the 0 polynomial, because what happened? So every single term I pick up over here in this definition, there'll be at least one guy which is 0. There is no perfect matching. Each one of them turn out 0. Therefore, it's identically the 0 polynomial. But on the other hand, if G has a perfect matching, then what? Then could it still become the identically 0? Can there be cancellations in it? In this case, you know that it was if there's no perfect matching, of course it is identically 0. If it had a perfect matching, can there be, therefore, if it had a perfect matching, when sigma corresponds to that particular perfect matching, you will pick up those terms. Can it get cancelled with anything else?
No.
Because you're choosing a different set of variables each time. Therefore, in this case, I want to claim that determinant AZ is not 0, and furthermore, what is the degree of this determinant of AZ? What's the max?
N degree polynomial.
It's a degree n polynomial. So now checking if it's has a perfect bipartite matching or not just amounts to checking if this determinant is the identically 0 polynomial or not the identically 0 polynomial. And how do you do it? Just pick a random point and just evaluate it and check it out. So this just tells you, so to check non-zeroness, rather to check existence of bipartiteness, existence of perfect matching, this is equivalent to det AZ not being 0. And we have a randomized algorithm, a very simple randomized algorithm. Just choose yes. So just choose. So let's just set S to be some subset of the field. This can be the rationals, this one, whichever finite field you're choosing. Choose some set of the rational field. Just choose yes to be several orders of magnitude larger than n, the degree. So let's take it to be, say, 100n. Then it's clear that if G has a perfect matching, the probability when you pick a random S from S to the, this is n choose 2. Determinant of A bar is 0, this will be less than or equal to n by size of S, which is less than 1 by 100. Whereas if G has no perfect matching, the same probability is 1. So this randomized algorithm, the use of randomness was checking if two polynomials are, it lets you check if the graph has a bipartite matching or not in such an easy fashion. This is far, far simpler than the deterministic algorithms that you would have seen possibly in an algorithms course, where to find out if the graph has a perfect matching or not. It's far more involved. Just if you have the power of randomness, we can just check, compute this determinant, choose a large enough set of points, go to any field. Now, you work with any field in which the number of elements in the field is at least 100 times n. So choose a large enough finite field or work with the rationals or whatever this one. Choose such a set and just pick a random point in it and check it out if the thing evaluates to 0 or not. And this tells you, to check. It's not a deterministic algorithm. So it's not an algorithm that always is correct, but with high probability, it's going to give you the right answer. And this should actually surprise you with the amount of power randomness has. The previous thing which we said, checking of polynomial identity testing, lends itself so easily. It gives you such a simple algorithm for bipartite perfect matching. And by the way, this is one of the cases, and it's goals of this course, this area of research. This is one of the algorithms we'll see as the course proceeds, which we have not been able to eliminate randomness completely. In fact, polynomial identity testing is a problem for which we haven't been able to eliminate randomness, and we'll see some algorithms where you are able to eliminate randomness, some places where we're not, and this is one thing which actually still defeats all our attempts at trying to get rid of randomness in its entirety. Okay, any questions?
So here, I don't think we are going to compute this determinant, these n factorial computations when we are calculating.
No, I forgot to mention that. So determinant computation, this is the definition of determinant. I should have mentioned that. So thanks for pointing. This is the definition of determinant. This is not the definition. When we compute determinants all the time in linear algebra, we don't use this definition to compute the determinant. This is a horrible definition to compute determinant because this is a summation that goes over n factorial things. The way we compute determinant, one way to do it is Gaussian elimination. Take the matrix, sort of make it upper triangular or something, and then just take the product of the diagonals. This one, that will give you. And these are actually very fast. These are running in time order n cube. So there are other algorithms that compute determinant much more efficiently. In fact, this is a polynomial time algorithm I told you. There's also things, if you work in complexity, they're extremely parallel algorithms that compute determinant. So in some sense, this says it gives you a very parallel algorithm to check if a graph is matching or not. That's not the point of it. This just shows if determinant is something which we compute easily. Determinant is an easy object to compute. It's not via this definition. But it's using other linear algebraic techniques. Just Gaussian elimination will tell you how to compute determinant. There's an order n cube algorithm. Use that algorithm to compute determinant instead. Don't use this definition. And when you use that, that lends itself to the randomized algorithm we just now suggested.
Okay, thank you.
Yeah. Any other questions? I finished the first item in my today's agenda. I had 4 items on the agenda. No, but I think it's good that you spend time on finite fields. This is an important thing we will need. Good. Any questions on finite fields or the polynomial identity testing lemma, the Schwartz-Zippel lemma, or the application to by perfect matching? This is one of the most stunning applications of randomness. How randomness comes. You will realize that in check a bipartite matching, check in a bipartite graph, perfect matching exists. You could use randomness and in such a clever way. Yeah, this doesn't convince you of the power of randomness. I don't know what will. Yeah. Any questions? Okay. So we'll stop with this. I'll do one more application next time, and we'll begin asking how essential was randomness in some of these applications and see if we can eliminate randomness or reduce the amount of randomness that we used in some of these applications that we saw for last lecture and this lecture, starting from next lecture onwards. Okay, we'll stop with this.
Prahladh, a small thing. So that is n choose 2 or n square exactly?
Sorry, you might be right. N choose 2 was, this would be n squared. Actually, see, it's neither of them. It is actually size of E.
Right.
Yeah, the size of E. Yeah. That's the dimension, number of variables we have. For every edge, we have a variable, and there are E edges.
Right, right.
Okay, now we'll stop and meet on Tuesday.